Hello and welcome to the second part. So in the second part we're going to look at basically we're going to continue what we've just been doing, but here in this case we'll have to uncover the functions for ourselves. So basically we're going to do some economic application. So basically we're going to try and optimize profit, we're going to try and optimize revenue, we're going to look at tax and how that kind of stuff influences. I'm going to make only a couple of exercises to basically get you going, but again, I strongly recommend that you try to make all of these because, basically you as future economists, this is important that you know how this works and that you can kind of imagine how these things interact with one another. So the question 4 I'm going to leave for you. It's optimization of a farmer with a wire, very classical, I would say mathematical question. Basically you just need to see that you have to optimize your volume and that your volume is somewhat restricted and you know something about it. But I'll let you do that at home. So that being said, let's move on to question number 5. So for question number 5, we know a couple of things. We know that the price of our good is equal to 400 minus 0.4 Q. So price is dependent on quantity, and we have a fixed cost of 2000 and we have a variable cost of 160. So first things first, what are we asked to do? At what price does the producer need to sell his goods in order to maximize his revenue? So here we first need to find, a total revenue function, and then we need to optimize it. So the first things first, total revenue is nothing more than, the price that you sell each goods for times the quantity of goods you have sold, right? And this is really great because we have a function for our price and, quantity, we'll just keep it as quantity. So we say our total revenue in this case, we'll call this sub-question A, it is 400 minus 0.4 Q. I'll try to do a different type of notation because my Q's tend to really look like 9s. So I'm sorry if I confuse you during the class, but basically times its quantity, and then here times quantity. So what do we end up with? Well, we end up with a function that looks as such, 400q minus 0.4q squared. Okay, now we're interested in optimizing this. And what do you remember? Well, if we want to optimize it, this is going to happen where our first order the derivative is equal to 0. So that means we take our total revenue function and we derive it. So that little accent means that. So what do we get? We get 400q minus 0.8. Sorry, not 400q, it would just be 400 minus 0.8q. So that's the derivative of this. And this needs to be equal to 0. And doing a little bit of arithmetic, what do we find? Well, we find that 0.8q needs to be equal to 400, or in other words, it tells us that q, so our quantity sold, needs to be equal to, in this case, 500. Okay, so this is great, but now we need to check, is this a maximum or a minimum? Because that's very important, right? If this were a minimum, so this would tell you, this is the quantity that will minimize your revenue, that's not really that interesting. So in this case, of course, you see that it's a second degree polynomial, so you could kind of guess at its shape already, but let's try this. So in this case, I think the quickest way to do this is we just take a second order derivative of our total revenue, and we find that that's equal to negative 0.a, which is smaller than 0, telling us we have a maximum. Okay, and then I might hear you wonder, is this a local or maximum, or is it a global maximum? Well, you will see in these exercises, these functions tend to be very neatly behaved, and most of the time actually are only second degree polynomials. So we know that they either have this shape or they have this shape, right? So in identifying one of these points should be enough. So of course, if you do have a function like this, then I want you to think a little bit further, but most of the time I will give you bounds then to think about. Okay, so we know that we have a maximum over there, but we haven't found our entire solution yet. Now we're interested at, we know that we're going to get a maximum when we sell a quantity of 500. What does the price need to be then? Well, the price is equal to 400 minus 0.4 times our quantity at that point, so 500, which is nothing more than telling that our price needs to be equal to 200. Okay, so that's for sub-question A. Now let's have a look at B. And here we're interested in optimizing our profit. And you'll see profit, I'll write it as a big pie. So how can we do that? Well, that's total revenue minus total cost. So total revenue, we already know how to find it. That's price times quantity. And then minus the total cost. Well, what's total cost equal to? Well, total cost is equal to fixed cost plus variable cost, right? So if we were to rewrite this, what do we get? Well, first things first, we already know total revenue. We've already calculated it once. We know that it's 400Q minus 0.4 Q squared. And then, well, we need to be careful about this, well, total cost function. Well, we have here fixed cost, and our fixed cost is equal to 2,000, so minus 2,000, because, well, it makes sense that we're subtracting our costs. And then here, a little bit of an asterisk. We have to be careful, because here I said, well, the variable cost is 160, but what does this mean? It means that for each quantity extra sold, so every time we sell something, we're going to have to pay 160. So what does that mean? Well, it means that this is actually, if we were to write the total cost function, it would look like this, right? It would be 2,000 plus 160 times the quantity sold. So here you get minus 160Q. Okay, let's do some arithmetic and simplify this a little bit. So we get 0.4 Q squared. Then here, let's bring these two together. So what do we find? We find that that's plus 240Q. 240Q. And then here we find it's still minus 2,000. Okay. If we have this, well, now we can start optimizing this. Again, what do? We just take our derivative of this. So our derivative of this would yield us minus 0.8 Q plus 240. And what else do we know about it? It needs to be equal to 0 at that point. So in other words, it tells us that Q needs to be equal to 300. Again, let's evaluate whether this is truly a maximum or a minimum. How do we do that? Well, we could take, again, the second order derivative. Of course, you could have already seen, well, it's the same kind of function as over here, so you would already know. But here you get, well, the second order derivative is negative 0.8. Again, it's smaller than 0, so we find that that's truly a maximum. Okay, now that we know that, well, we're still interested in what does our price need to be. Well, we fill that in. 400 minus 0.4 times 300, or in other words, it tells us that our price is 280. Okay, now let's go to C. And in C, we're interested in knowing about our marginal revenue and marginal cost. And, well, I've already talked about it a little bit, but our marginal revenue, what's that going to be? Well, our marginal revenue is just our total revenue derived, and then we have our marginal revenue. And just the same for our total cost. We're going to derive that, and then we'll get our marginal cost. So let's try that once. So we know that looking from here, our total revenue, well, was P times Q, so we got this over here. We have actually already derived that one, so we can just copy it, so it's 400 minus 0.8 Q. 8Q, right? Or in other, and here, well, for our marginal cost, well, basically if we derive this, all that we're left with is 160. So marginal cost, let's evaluate it at the point we're interested in. So at a quantity sold of 300, because it's a constant function, we'll just know that it's 160, and our marginal revenue evaluated at 300. Here we do need to fill it in a little bit. We get 400 minus 0.8 times 300, and again, what do we find? It is 160. So what do we see? That when our profit is optimal, these two are equal to each other. And this makes total sense, right? Because let me rewrite the function again a bit. So we know that profit is equal to total revenue minus total cost. Okay, if we derive that then, and we know that we want to know the optimum of it, so our derivative needs to be equal to 0. If we go down, well, if we derive this piecewise, what do we get? It's marginal revenue minus marginal cost. Or in other words, rewriting this a little bit, we find that marginal revenue needs to be equal to marginal cost. Okay, so this for question 5. Then 6, 7, 8, and 9. I encourage that you have a look at those at home. I'm going to explain a couple of things in future examples that you might find some instructions on how to tackle those problems if not immediately clear. So don't despair. Look at the couple other examples I'm going to discuss and then try these as well. So we're going to go to question 10. And for question 10, we know a couple of things, right? We know that we have a demand function and we know that we have an average cost function. So here we have a demand function that is Q is equal to, well, no, let's wait before I rewrite it. I'll immediately just say I'll rewrite what I wrote here. So we know that Q is minus 90 plus 2p is equal to 0. And we have an average cost function that is Q squared minus 8Q plus 57 plus 2Q. Okay, so now we need to rewrite this a bit so that we have something about it, because, well, what are we asked? We're asked to find, well, the level of production that maximizes revenue, so our quantity. Okay, so if we look at this, we need to get something useful out of this because we want to calculate total revenue, and remember, total revenue is just price times quantity. So we want to find some kind of expression for this, and well, we were interested in finding the Q value for where it's optimal, so I think it would be interesting if we read everything in terms of Q. So that means, well, we're interested in distilling this into something that where we get information about the price function. So we know that P, in this case, bringing everything else to the other side, we find that P needs to be equal to minus Q, and let me do that really differently, because, well, so this is Q, and let me rewrite those Q's as well, so that nobody gets confused, that I'm actually writing 9s. I think this is clear. So P needs to be Q over 2 plus 45. Okay, great. Average cost, we don't need that for now, so we can skip it. So that means our total revenue function, in this case, it is negative Q squared over 2 plus 45Q. Okay, now, well, we want to optimize this. Well, what do? Well, we first derive it. So our total revenue derived, what's that going to look like? Well, these two, we drop it. That gets neatly cancelled out by this 2, so we find that it's negative Q plus 45 needs to be equal to 0. Or, in other words, Q is equal to 45. Let's verify if this is truly a maximum or a minimum, and then we can say, well, total revenue, derive it twice, we find that that's negative 1, smaller than 0. We find that this is, yes, indeed, a maximum. So we can just keep this, and we say that this is the quantity that we need to sell for to optimize our revenue. Okay, then let's look at B. And at B, we're interested in finding the amount of production that maximizes profit. Okay, so we need to find a profit function, but, well, we're kind of stuck because we don't have a total cost function. But we do have an average cost function. And, well, the average cost function is just your total cost function derived to the amount of quantity you've sold. Well, not derived, divided by the amount of quantity sold, right? It's just an average amount, the amount of goods that you've sold. So, well, if we want to go from average to total cost function again, well, we just have to multiply it, right? Multiplying both sides times Q, you get this. So we can go a little bit further for this, and we find that our average cost function looks as follows. No, sorry, not our average cost function, our total cost function looks as such. It is Q to the power of 3 minus 8Q squared plus 75Q plus 2. Okay, now that we have all of this, well, we can use it to write our profit function. So our profit function will look as such. Total revenue, which was minus Q squared over 2 plus 45Q. Let's go a little bit further. What do we find? It is here minus Q to the power of 3, because remember, we're subtracting the total cost, plus 8Q minus 75q, and then minus 2. Okay, we can rewrite it a little bit and simplify this, and we find that this is negative q to the power of 3 minus q squared over 2 minus q squared over 2. Oh, I think I forgot something over here. Yeah, I forgot here the squared. So it is not minus q squared over 2. It would be minus, it would not be minus. So it would be 15 q squared over 2 minus, then what do we get? We're still left with negative 12q, and then just the 2 by itself, minus 2. Okay, so we're trying to optimize this. Again, what do? Well, we take our derivative and equal it to 0. So we know that negative 3q squared plus 15q minus 12 needs to be equal to 0. For this, well, what can we do? Well, we can look at our discriminant. But first, let's rewrite it a little bit to make it as easy as possible. So we can say we bring out 3, we get q squared minus 5q plus 4. Okay, that's the one we're actually trying to solve where it's equal to 0. So we say, okay, the discriminant in this case, it is negative 5 squared minus 4 times 1. Or in other words, our discriminant in this case is going to be equal to 9. Okay, that tells us a couple of things. Our x1 and x2 value. Well, what does it tell us? It tells us that x1 2 is equal to 5 plus minus 3 over 2. So in other words, we get 2 points of interest. We get the point 1 and the point 4. Okay, now we're interested in, well, is this a minimum or a maximum? Where do we have a minimum and a maximum? Okay, let's evaluate that then. So we draw this thing, and here we get x and fx, because, well, we can of course derive it once more, but I think maybe in this case this is faster. Not necessarily, but it depends what you're most comfortable with. You know that it's 0 over here. Then, well, let's evaluate it at 0. We know that it's going to be negative. Then in between it's going to be positive, and then here it's going to be negative again. What does this mean for our function? Well, it means that our function first goes down, then it goes up, and then it goes down again. So here we're going to have some type of minimum, and here we're going to have some type of maximum. Okay, here, well, to pay some stuff in mind, well, we need to kind of look at this. Like, what does this mean? Well, it means that our function is going to go down, 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 down. So actually we have something like this, right? Function shaped more or less like this. You'll see if you were to draw it, it would kind of look like this. So our function goes down, we hit kind of like a minimum, and we see that, well, it's just going to be a local minimum, right? So over here, there might be points that are more interesting relatively to the maximum, and here there are points that are more interesting relative to the minimum. Well, not really more interesting. So in this case, yeah, you could say you produce over here, but really the thing you want to consider is, well, imagine that we produce nothing. What would happen to our function? And we see that in that case, so our profit function, if we sell nothing, we fill all of that in, we find that we sell just diddly squat nothing. Then you can evaluate the function again for 4 and see what you get. And then you can make an inference about, well, what is this? Is this truly interesting or not, this point over here? Is this truly an interesting maximum? I'll leave this as an exercise for the reader at home. Okay, then we can move on to the last question of number 10. And here we're interested in where marginal costs are as low as possible. So let's again find our cost function. We find that our cost function looks like this. We're interested in our marginal cost. So our cost function was, let me rewrite it again, it's q to the power of 3 minus 8q squared plus 57q plus 2. Okay, this is our total cost function. Now we have to derive it, so our marginal cost function is 3q squared minus 16q plus 57. So this is going to be our marginal cost function. And now we're interested in knowing where this is going to be maximum. Well, again, we're going to have to derive it once more, right? Because now this is the function we're trying to optimize. So what do we need to do? Well, we derive it one more time. So we get the derivative of our marginal cost function, which is going to be equal to 6q minus 16. Or in other words, this is going to happen where q is equal to 8 over 3. So this is great, and we're trying to minimize this marginal cost function, so we need to derive it once more and see what we're dealing with. We see that that's equal to 6, which is greater than 0, which tells us this is a minimum, as was desired. So you can keep this over here and say this is your final answer, because we're just dealing with a second degree power. Okay, so I think this is pretty much everything for question number 10. Then let's do 2 more. One where we're going to consider taxes and one where we're going to consider some other stuff as well. So first we're going to go on to question number 13. Let me pick a new slide for that. Question number 13. And here we know a couple of things. So the demand for a certain good is equal to the next thing. I'll write it down. So P is equal to 14 minus 3Q. And we know that our total cost is equal to q squared plus 5q, right? Okay, so if we read this and it says, assume the taxes are imposed on the producer for each unit sold, which makes sense, right? When is the last time you went to the store, bought something, and you had to pay, well, taxes immediately to the government? Well, no, most of the time it's the producer that takes care of that part. So then we're interested in calculating the maximum profit, the price change as a consequence of the increase in tax, and the amount of taxes receivable by the company. So if we were interested in the maximum profit, well, and we're interested in, well, the price change and that kind of stuff, well, we have to calculate a couple of things first. While it's not immediately asked, we're first interested in, well, what's our product? Imagine that there was no taxes. So I'll write it like this. No taxes. So again, we get that that's P times Q minus our total cost function, which in this case I'll just write immediately, 5Q. Let me fix that. So Q, I'll write it like this. Okay. If we have this, well, what do we get? We can rewrite it a little bit. We get 14Q minus 3Q squared minus Q squared minus 5Q. Or in other words, our profit function in that case is minus 4Q squared plus 9Q. So now we're interested in optimizing this. So we take the derivative of this, the derivative of our profit under no taxes. What do we get? This needs to be equal to 0. We get minus 8Q plus 9 needs to be equal to 0. Or in other words, Q is equal to 9 over 8. If we were to verify whether this is a maximum or a minimum, we just derive this one more time. We find that that's equal to negative 8, which is smaller than 0, which tells us we have a maximum. Okay, so that's for the first part. So that's our quantity sold if there were no taxes. Now let's consider what would happen all of a sudden if taxes get imposed. And here I'm going to make a little thing, like I'm going to make a little change. So where would taxes be imposed in this entire thing? Well, taxes would be imposed as some kind of cost for the company, right? They have to pay these taxes. But it's a little bit more subtle than that because, well, it's not really a lump sum. It is imposed on every amount that they sell. So, well, what would happen is, well, you get some kind of taxes for a certain amount of T, which is the price of tax per unit sold, times each unit sold, right? So this is the tax case. Okay, then again, let's optimize this. So we say, okay, our profit under taxes, what do we get now? Well, we get that that's still 14Q minus 3Q squared, but now, well, this becomes a little bit longer. We get it is still minus Q squared minus 5Q minus T Q. Again, let's rewrite it a little bit and we'll see we'll get something very similar to what we found before. We know that it's minus 4Q squared. and then we get that it's plus 9 minus t times q. So this is our profit function if there are taxes. So, okay, let's calculate that because, well, in the end, we're going to evaluate what was the change, right? So we take the derivative of this, we say, well, that needs to be equal to 0, so we find that it's minus 8q plus 9 minus t. And you see this is very similar to what we found before. So we see that now q needs to be equal to not to 9 over 8, but 9 minus t over 8. Okay, so now that we have these quantities, well, we're interested in, well, what is the true effect of imposing this tax? Or what is our profit in this case, right? Because we have to calculate the maximum profit under tax. And then we also are later interested in the price change. So let's first calculate, well, what does this mean for our profit? So basically what do? We say, well, we evaluate our tax profit, our profit function under tax at point 9 minus t over 8. So we fill all of that in, so we get minus 4 minus 9 minus t over 8, and all of that squared, plus 9 minus t times 9 minus t over 8. Okay, great. We can work around a bit with this, right? Because here we get, well, it's going to minus 4 times 9 minus t squared over 64 plus 9 minus t squared over 8. Okay, again, we can rewrite this a little bit further. And what do we find? We find that this is going to be equal to 9 minus t over 16 and the numerator squared, of course. So this is going to be our profit under taxes. Great. So here, all we need to do is now the government needs to tell us, well, we're going to impose 0.5 euros per quantity sold. We can just fill it in and we immediately know, well, what our profit is going to be because, well, here, this is a 9, of course. Okay, so let's have a look at the total price. Well, what is the total amount of taxes that the government can receive? Well, it's this part, right? It's the price of the tax times the quantity sold within that economy. So we can say the total tax is just t times 9 minus t over 8. So if in another exercise you have to calculate, well, what is the optimal price for the tax? Well, all you would have to do is this. Well, so I'll write a tax total here. All you need to do is then derive this, right? Because then it will allow you to find, well, where this function is going to be maximum for what value of t. So if you were to maximize this, you just take the derivative of that. And it will allow you to maximize it. But in this question, it wasn't asked, so we're not really going to look at it. But I know in other questions, it is asked. Okay, so that's the amount of taxes receivable by the government. Now, well, I know I've been dancing around it a bit, but we are interested in the price increase. Let me do that here so I can just quickly use all that. So here on the thing. So we're first interested in what was our first price. So our first price is just the price if there were no taxes. So what do we get? Well, we found that our optimal strategy was selling this amount. So we just need to fill it into this function over here. So in other words, we find that our first price is 14 minus 3 times 9 over 8. 9 over 8. Okay, let's leave that like that for a bit. And here we get, for our second price, well, we have now a little bit of a different thing. We find that our optimal quantity to sell was this. And again, we fill it in over here. So we get that is 14 minus 3 times 9 minus t over 8. If we split this up a little bit, it will allow us to compare these things more easily, and then you will also see why I didn't work this out. Say 14 minus 3 times 9 over 8 minus 3 times t over 8. Here or a negative sign. So in other words, what is our going to be? Well, our price change. Well, our price change is completely going to be encapsulated in this part of the function because that's the only part that's new. So in other words, our price change, so our delta price is going to be equal to 3 times the amount of tax over 8. Okay, so this is basically our answer. We found here we find our profits, the amount of taxes received by the government, and here we find the price change. Okay, let's make one more application, and I struggle a bit to call it an economic application because it's not really, but it's a good exercise to know and to kind of think about, well, optimization and in what other ways this can be useful. And we go to question number 15. And what this tells us? Well, it tells us that there is a lifeguard somewhere along the beach and that there is a person in the sea in need for aid. And we know a couple of things. Well, we know the position of this person relatively to the lifeguard, and we also know that the lifeguard is a faster runner than a swimmer. Okay, let's bring all of this information together. Well, we know that there is somebody in the sea sending an SOS to the lifeguard. What do we know about this person? Well, we know that they are about 100 meters into the sea. Another thing we know is that they are 300 meters removed from the lifeguard if we just count along the shoreline. So like this. So here we have our lifeguard. And now our question is, well, if we know that the lifeguard is a faster runner than a swimmer, well, then we have to say that, well, on land, the lifeguard, in this case, we know that he runs 5 meters per second, and in sea, he is a little bit slower with 3 meters per second. And now we're interested in finding, well, what's the optimal point for the lifeguard to basically jump into the water and start swimming for as quickly as possible to the person in need. Well, what do we see? Well, actually, we don't know exactly how far it is, but we can know that, well, if he once he jumps into the water, he will swim as fast as possible to the person in the water, and we know that it's going to be a diagonal line like this. Right. So, the question is, what's this point over here? Where does the lifeguard need to stop running and he jumps into the water? And goes immediately to this. And basically the hardest part of this question is, well, we need to make one very intelligent choice, basically so that we can rewrite it as a single variable function. And actually the clever choice here is to choose x here. So this is the distance x, so basically 3, and then this will be 300 minus x. Why is that the cleverest choice? Because, well, it allows us to express all the unknowns just using one variable. We know that here, well, this is the amount he didn't run of those 300 meters, so we know that here he needs to run that far. But thanks to Pythagoras' theorem, it also allows us to calculate how far he needs to swim, which is going to be x squared plus 100 squared, right? That's going to be that distance, and all of that, the square root of that. Okay, now we know that, we know our distances, and we know our speed, we can actually make an inquiry about how long he's going to run. So I'll call it time, and maybe I'll give it a big T, total time. So how long is he going to run about this? Well, he's going to run only 300 minus x meters. So 300 minus x meters. And then we're interested in, well, how fast is he there? Well, and we know that he's 5 meters per second. So how long does he do about that? Well, for that we need to divide it by 5. Okay, why does this make sense? Let's look at these, well, what these units say. Well, so this is meters, and this is meters per second. I know this looks like a high school physics class, but basically, well, these are neatly going to cancel out. Seconds is going to move up to the top, and we get an expression in terms of seconds. Okay, so that really, as a quick side note, let me remove those things. Basically, we don't need it for our calculation, but it's good to know why we're doing that. Okay, so that's how fast he is for the piece on land. So that's how much time he spends there. Then we say, well, he spends, of course, a little bit more time because, well, he still has to run this distance. Well, not run this distance, he still has to swim this distance. X squared plus 100 squared. So in this case, we're going to divide that by 3. So this is basically a function that we have made to identify how long he's going to run/swim over it. Okay, and now we want to minimize this. So what do we do to minimize this? Again, we take the derivative and equal it to 0. So we take the derivative, so total time derived, and put it equal to 0. So what's going to happen over here? Well, the 300 divided by 5, which is just 60, just going to remain what it is, but minus x over 5, it's going to become minus 1 over 5. And then here it's a little bit trickier. What do we find? It's 1 over 3 times, and then here, let me open the brackets, it's going to be 1 over 2 times that square root. Not forgetting about the chain rule, because the chain rule tells us we still have to derive everything that's underneath the chain, the square root, which tells us that it's going to be 2x at the numerator. We can cancel a couple of things out, and this is our new expression. Okay, great. Let's work a bit with that. So we can say, well, in this case, we can say that 1 over 3 times, let me immediately rewrite it differently. Let me make the numerator a little bit wider. So we say 3 times the square root of x squared plus 100 squared, and in the numerator x needs to be equal to 1 over 5. Great. That means that we can cross this thing, right? Everything in the numerator moves here. The denominator goes to the numerator, and this moves to the numerator over there. So what do we find? We find that 5x is equal to 3 times the square root of x squared plus 100 squared. Okay, if we want to solve this, we need to square it. We need to square both sides, but careful. If you want to square both sides, we have to make sure that we're checking our power conditions. And in this case, we do have a power condition because this can be negative. So what do we need to say? Well, our power conditions tells us that 5x needs to be greater or equal than 0, or in other words, this means this only happens when x is greater or equal than 0. So if you find a solution where this doesn't abide, of course, negative distance in this case don't really make sense, but well, you could argue that it needs to run further beyond the point that we drew. We need to use this over here. So, okay, once we have this, we can square both sides, and we find 25x squared is equal to 9 times x squared plus 100 squared. Okay, great. So we find here that that's 9x squared plus 9 times 100 squared. And here we get 25x squared still. Moving all of our x's to one side, we find that over here we are left with 16x squared is equal to 9 times 100 squared, which of course is 10,000. And then we get here that x squared is equal to, if we work everything out and divide it by 16, we find that that's 5,625. Okay, great, we're almost there. Now we just need to square both sides, and we find that x is equal to the plus minus square root of 5,625, or in other words, it's equal to plus minus 75. Okay, let's check our answer with our power conditions. And our power condition told us that x needs to be greater or equal than 0, so that means that this is not a valid solution. So we only know that it's 75 meters. Reinterpreting what we just found, so we know that this is 75 meters. It tells us that our lifeguards needs to start swimming at 225 meters. That's the moment he jumps into the water and starts swimming to the person in need of rescuing. Okay, this is it about optimization problems and that kind of stuff. Now I'm going to move on to integrals into the next video. So I strongly recommend you make the other exercises so you can practice on these kind of economic problems. We normally always ask one on the exam, so it's good that you practice. Okay, see you in the next video. Bye bye.